Welcome to this video on electric potential and potential energy. Before we get into potential and potential energy, we should have a quick review of work and energy. We're going to need to remember that work is defined as the product of the displacement and the amount of force that is parallel to our displacement. That is, that work is Fd, and the units for work is a joule, or R a joule, or a Newton meter. We also have two different types of energy that we're going to talk about here. We have the potential energy, which is the ability to do work by definition or by virtue of where you are, and kinetic energy is the ability to do work by virtue of what your motion is. Both of them are in units of joules. When we're talking about potential energy, we're talking about the work required to move a charge. So let's imagine that we have a positive Q source charge and a positive Q test charge. If I wanted to know the work required to move our charge from plus Q, or to move our charge from A to B, I would have to look at the distances in between the difference in distances between A and the charge and B and the charge. That is, look at the radius at which A is and the radius at which B is. So at A, our electric force is kQq over Ra squared. That's Coulomb's law. And at B, our force is kQq over Rb squared. So in order to figure out the force that is exerted on the charge from here to here, I have to actually take a look at the average force because the force changes. So by using some algebra, remember that average is 1 plus the other divided by 2. If I add these two together and divide them by 2, I get the result force average is kQq over Ra times Rb. Remember, the distance then is Ra minus Rb, because that's from here to here. And so the result is that my work is kQq over Ra times Rb multiplied by the different distance there. Using another little trick of algebra, I get this as my work. So the work required to move a charge from one location to another is given by that equation right there. That's useful if we know our two different locations, but sometimes we just want to know how much is the potential energy at a point. So we define something called absolute potential energy, which is the potential energy at a given point. And the reason that we define it as absolute is because it's relative to an infinite location. It's the amount of energy that would be required to bring it from infinity to that point near our charge. So the absolute energy at point A is the amount of energy required to bring it from infinitely far away to point A. So if we're trying to find it in this example here to Rb, our work is given by that equation. If we're having an infinitely far away initial location, that means that that term goes to 0. 1 over infinity goes to 0. And so the result is we have this equation for absolute potential energy. It's a very important equation for you to know, and it should look very similar to a lot of the equations that we've been working with so far. So go ahead and make sure you write that down. So let's do a practice problem. What's the potential energy of a 2 nanocoulomb charge moving from an infinitely far away to a point A, which is 8 centimeters away from a plus 6 microcoulomb charge? Go ahead and pause your video and come right back. And so we can take a look. Our potential energy is given by that equation there. And so if we plug in all of our values, our test charge is 2 nanocoulombs, our source charge is 6 microcoulombs. So the result is that our potential energy is 1.35 millijoules. Now, because they're both positive here, that is important. That is important. So we're going to talk about that next. It's a positive potential energy of 1.35 millijoules. So the signs for potential energy have to do with whether or not we are going to be increasing or decreasing our potential energy. That is, whether or not the field is going to be doing work. So at point A, our potential energy was positive. If we went to then point B, the question is, does the potential energy increase or decrease? So the field will do either positive or negative work, and the potential energy will either increase or decrease. So moving from A to B, the field does positive work because the field points out and our displacement is out. So the force is out. So the force and the displacement are in the same direction. So we have positive work. So therefore our potential energy decreases. If it moves from A to C instead, the field does negative work and our potential energy will increase. Okay, so take a second, make sure that that makes sense. If the field does positive work, our potential energy will decrease. That is, our potential energy is smaller at B than it is at A. And if the field does negative work, our potential energy increases. That is, that we have more potential energy at C than we do at A. Now, we should remind ourselves that we've talked about electric field as a property of space that allows us to figure out the force on a charge at that location. Our electric field is given by force per charge. That is, that we can predict the force by taking our charge and multiplying it by the electric field at that point. The field exists independent of the charge and is found by this equation. KQ, big Q, where Q is the source charge here, divided by R squared. We have a similar concept that has to do with potential energy instead of force. So the electric potential is another property of space. It exists independent of what's there, and it allows us to figure out the amount of potential energy that any charge will have at that point. So electric field allowed us to figure out how much electric force there would be. Electric potential allows us to figure out how much potential energy there will be. So we define electric potential, that symbol is V, as potential energy per charge. That is, U equals Q times V. And the units are joules per coulomb, right? Joules are the units for potential energy, and coulomb is the unit for charge. So for example, if we had a potential of 400 joules per coulomb at point P, a negative 2 nanocoulomb charge would have this much potential energy. Negative 800 nanojoules. It's a predictive property. We redefine that unit of joules per coulomb as the volt. So the volt is equal to 1 joule per coulomb. So that means that 1 volt is the amount of, it tells us that 1 coulomb of charge would have 1 joule of energy at that point. So if we had a point where the potential was 1 volt, that means a charge of 1 coulomb will have 1 joule of potential energy at that point. So in order to calculate the electric potential, we know that U is given by KQ over R, and voltage is U divided by our little q. So we find that our q's cancel out, and we're left with the fact that our potential, electric potential, is KQ over R. The electric potential, because of a positive charge, is positive, and because of a negative charge is, I'm sorry, that's incorrect. This should be negative. The electric potential due to a negative charge is negative. So if, for example, we wanted to find the potential at a distance of 6 centimeters from a negative 5 nanocoulomb charge, we could do that because we know that it's KQ over R, so it's 9 times 10 to the 9th times our charge divided by 0.06 meters, which means that we have negative 750 volts of potential at that location. That means that we could find the potential energy if we placed a charge there by multiplying our charge by the potential, and we would get that the potential energy there would be 3 millijoules if we placed a negative 4 microcoulomb charge there. Remember, our potential energy there is positive because that means that our electric field would do positive work on that object. If we have multiple charges, just like before, we can add up the potential of the multiple charges. And so because this is not a vector, this is just a scalar, we add up just the algebraic sum due to each charge. And so here's an example of that. If we have these two charges, Q1 and Q2, we want to calculate the electric potential at point A. We have to add together those. So at point A, because of Q1, we would have 450 volts. At point A, because of Q2, we would have negative 2250 volts. So the net voltage, or the net potential, is negative 1800 volts. The final thing I want to talk to you about is this idea of potential difference. The potential difference is literally just the difference in electric potential between points A and point B. It's the work required to move, work per charge required to move from point A to point B. And so it's the voltage at A minus the voltage at B. So it's the work done by the electric field per charge, Q times VA minus VB. And what that does is it gives us the ability to calculate the electric potential between two parallel plates. And this is where I will leave you.